What specific problem do shortcut models aim to solve in the context of generative modeling, and how does this problem relate to existing iterative denoising methods?
Shortcut models aim to solve the problem of expensive inference associated with existing iterative denoising methods, such as diffusion and flow matching models, which require numerous forward passes of the neural network to generate high-quality samples. These traditional methods often necessitate dozens to hundreds of iterations, leading to slow and costly generation processes. In contrast, shortcut models enable high-quality generation in a single forward pass by conditioning the model on both the noise level and the desired step size, allowing it to effectively jump ahead in the denoising process. This approach eliminates the need for complex two-stage distillation or careful training schedules, making shortcut models more efficient and capable of handling various sampling budgets without sacrificing accuracy. Empirical evaluations demonstrate that shortcut models can match or outperform the quality of samples generated by baseline diffusion models, while significantly reducing inference costs.
How does the proposed shortcut model algorithm work? Can you illustrate the process step by step, particularly in terms of how it conditions the model on the desired step size and its impact on generation quality?
The proposed shortcut model algorithm operates by conditioning the neural network on both the noise level and the desired step size during training. This allows the model to effectively jump ahead in the denoising process, enabling it to generate high-quality samples in a single forward pass. The training process involves two main components. First, the model is trained using a flow matching objective at small step sizes, d = 0, which grounds the model's predictions to match the data denoising owed. Second, for larger step sizes, d > 0, the model utilizes self-consistency targets, where two consecutive shortcut steps are combined to create a target for a larger step size, thus propagating generation capabilities from many-step to few-step and one-step generation. This dual conditioning allows shortcut models to maintain high generation quality across various sampling budgets, outperforming traditional methods that require multiple training phases or iterative steps. Overall, the conditioning on the desired step size significantly enhances the model's ability to generate accurate outputs, even at low step counts, while avoiding common artifacts associated with naive flow matching approaches.
Can you provide a simple yet illustrative example of the main algorithm steps of the shortcut model? Walk through the example to clarify how the model achieves one-step denoising.
The shortcut model achieves one-step denoising by conditioning the neural network on both the current noise level and the desired step size. For example, consider a scenario where we have a noise point, x_t, and we want to generate a data point, x_1 in a single step. The model first samples a desired step size, d = 1/2, and then computes the shortcut, s_t td, which represents the normalized direction from x_t towards the correct next point, x_t plus d. This shortcut allows the model to effectively jump to the correct point in the denoising process, rather than making incremental updates as in traditional methods. During training, the model learns to generate these shortcuts by using a combination of empirical flow matching objectives for small step sizes and self-consistency targets for larger step sizes, ensuring that it can accurately perform one-step denoising while maintaining the quality of multi-step generations. Thus, the model can produce high-quality samples efficiently in a single forward pass.
What are the theoretical advantages of shortcut models over traditional two-stage distillation methods in terms of computational efficiency, accuracy, and ease of training?
Shortcut models present several theoretical advantages over traditional two-stage distillation methods. Firstly, they are computationally more efficient as they eliminate the need for extensive synthetic dataset generation and multiple training phases, requiring only approximately 16% more compute than a base diffusion model, compared to the significant computational costs associated with distillation methods that involve numerous forward passes and teacher-student networks. Secondly, in terms of accuracy, shortcut models maintain the performance of baseline diffusion models on many step generation while consistently matching or outperforming two-stage methods in few and one-step settings, demonstrating their robustness across varying inference budgets. Lastly, shortcut models simplify the training process by allowing for end-to-end training without the need for a carefully scheduled distillation phase, enabling indefinite training to continually improve performance without the complexities associated with specifying when to end training and begin distillation. This combination of efficiency, accuracy, and ease of training makes shortcut models a compelling alternative to traditional two-stage distillation methods.
How was the performance of shortcut models validated in the experiments? Describe the experimental design, datasets used, and the metrics or benchmarks that demonstrate the effectiveness of the proposed approach.
The performance of shortcut models was validated through a series of experiments that compared their generation capabilities against prior methods using the Celeba HQ256 and ImageNet 256 datasets. The experimental design involved training each model from scratch with the same architecture and codebase, ensuring a fair comparison. Models were evaluated on their ability to generate samples using 128 4 and 1 diffusion steps, with the Frechet inception distance, FID metric employed to quantify the quality of generated images. Results indicated that shortcut models demonstrated competitive few and one-shot generation capabilities compared to two-stage methods, while maintaining performance on many-step generation, thus showcasing their effectiveness across varying inference budgets. Additionally, the experiments highlighted that shortcut models outperformed alternative end-to-end methods and retained the ability for many-step sampling, further validating their robustness and efficiency.
What specific results did the authors achieve with shortcut models on both the Celeba HQ and ImageNet 256 benchmarks, and how do these results compare to existing methods?
The authors achieved competitive results with shortcut models on the Celeba HQ and ImageNet 256 benchmarks, demonstrating few and one-shot generation capabilities that rival prior two-stage methods while outperforming alternative end-to-end methods. Specifically, shortcut models maintained the performance of baseline diffusion models on many-step generation, achieving a one-step FID of 10.6 and a 128-step FID of 3.8 on IMAGENET 256. In comparison to existing methods, shortcut models consistently matched or exceeded the performance of distillation methods that require multiple training phases, while also significantly outperforming previous end-to-end methods across various inference budgets. The empirical evaluations indicated that shortcut models effectively handle many-step, few-step, and one-step generation without sacrificing accuracy, showcasing their robustness and efficiency. Overall, the results highlight the advantages of shortcut models in generating high-quality samples in a single forward pass compared to traditional iterative methods.